So yeah, thanks everybody for joining us today as the next webinar in the complex series. So today I'm going to cover data storage and file systems. But if you're new to complex, this is a new training program that's been funded by the National Science Foundation over the last 2 years here at SDSC, and the goal of Complex is really to teach end users of our supercomputers that we run about some of the skills and really the non-programming concepts and skills that you need to effectively use the types of resources that we provide at SDSC or the broader NSF-funded HPC community if you're a member of an access allocation. Right? And the goal really is to provide sort of general base knowledge that you can take to any of the systems in sort of NSF access HPC network. But yeah, so that's kind of the aim of the project. So today I'm talking about data storage and file systems, as Sandeep mentioned, and I'll go over sort of the concept here of the types of questions that we'll cover. But it's part of sort of a broader data management series that I'm trying to put together. And as I was going through the slides last day or so and trying to rework them a bit and clean them up, kind of, this has been for the last year and a half now, kind of the second talk in the series. I have a data transfer talk if you've attended that. There's a link to it, or haven't attended it. There's a link to a recording of that talk as well, instead of slides for that talk. But I'm kind of thinking moving forward that this talk might be the first in the series in the future. And just because it covers a lot of the sort of fundamental sort of definitions and concepts that sort of will sort of dovetail and help understand some of the issues we run into on the data transfer side. So just a caveat there that this might be the first in the series eventually, but right now it's the second. So if you've already attended the data transfer talk, I think having some of the knowledge here might be useful to understand some of the concepts there as well. Okay. Oop. And I do have the chat open on my side. So if you do have any questions as we go along, please feel free to, again, drop any questions you have, points of clarification in the chat there, and I'll try to monitor that as we go and stop at a few spaces. But there's kind of a lot of material. I'm still trying to whittle things down a little bit, so I might not get to every single slide, but I'm going to try to cover the broad sort of definitions and concepts that I want to get to today in today's talk. Get my timer up here so I can check the time. And again, as I think Cindy probably mentioned, we structure these talks to go for about an hour, and then if you have time, you can stick around for a half hour of sort of Q&A where we can talk a little bit more about either any of the topics I talk about today, or things that you want to ask about HPC in general. If we run out of things to talk about in terms of data storage and file systems. Anyhow. So yeah, this is sort of the goal for today's talk. I really want to cover what is a file system, because it's a bit nebulous, I think, if you're not a computer scientist by training or not an experienced sort of computational scientist, as maybe many of you are. So it's pretty important to understand sort of the general concepts and key terms around what a file system is and the different types that there are. And I'll get into talking about some of the most common ones that you'll run into on the types of HPC systems you might be working on, and what file systems are used for different purposes and why, and really give you, hopefully, eventually I want to get to, if you understand a lot of these concepts, you'll understand sort of this last question here of why metadata is sort of so important to understanding how to effectively use the different types of storage systems that you'll run into on the systems you're working on. And today, Yeah, the prerequisite knowledge here is sort of just a basic understanding of intermediate, Linux and shell scripting and things like that. Like I'll give you in this talk a few commands that you can run on Expanse, our HPC system, if you might have access to, or any other ones that you might have access to. Uh, they'll allow you to explore the different types of file systems you have access to on those systems. So nothing too complicated there. Okay, so this is sort of the table of contents. So what is a file system? So start at the beginning, right? So at the end, I mean, at the beginning, right, we talk about data storage, right? That's what we're trying to accomplish when we talk about what a file system is going to do for us, right? And just the basic definition of data storage, right, is the process of recording information on a storage medium. So it's both preserved and retrievable, right? And as humans, we've invented many different types of storage medium across time. And how we use those different physical storage medium for different types of data, has varied. But, as today we are mostly concerned about computer data storage. And so you'll notice a lot of those different types of storage devices you might be familiar with on the right-hand side. But as a general concept, data storage is very broad, and it can take on many different physical forms, right? And when we talk about storage on computing systems, though, we very intuitively understand sort of what a computer file is, right? That's usually what we're talking about when we're talking about storing data on a computing system, right? But as you dig deeper into sort of what a computer file is, which we will a little bit today, right? It really is a resource that you access, and in the case of writing and reading data from storage devices, right? And these files can have different formats, different encodings, uh, based on the type of data they're storing and designed to store, right? And if you dig a little bit deeper into sort of operating systems and things, and especially Linux, which is sort of native operating system used on HPC systems, right? Um, the whole concept of how the operating system works and everything that you sort of interact with is actually sort of file based, right? And there's different types of files and what they're used for. Um, so there is sort of this concept in the Linux world of sort of everything that you actually interact with is a file. So understanding what a file is and sort of how things are organized, on the systems you're interacting with is actually pretty much more complicated than your sort of intuition might, um, you know, give you. And so there's a lot to dig into here, which you can. A lot of Wikipedia links and things are given in all of these talks that you can click on and explore. But we'll try to, we'll mostly stick to sort of the basic concept of storing data in files and what a file system is here today. So what is a file system, right? So file system is effectively the software, right, that the operating system that you're working with, right, is using to organize those files on the storage devices, right? So kind of a little cartoon here, right? So that file system really sits between the operating system and the physical nature of the storage and the files and how they're stored on that physical medium, right? And those, as we saw on the first slide, right, that storage medium can be many different types of things, different technologies, not too important right now. But at the end of the day, a file system is trying to organize those files on the physical storage based on whatever actions you're taking on the computing system you're interacting with, right? And all file systems, right, support these sort of basic operations, which, are quite obvious, right? You want to create new files. You might want to change permissions of who can see different types of files. You have applications that want to open files and read data from files. You might want to write data to files, delete files, and close files, right? It's very, very straightforward. What you might not be familiar with, right, is some of the terminology around file systems. But in general, most of the file systems that you're familiar with interacting with are what are known as POSIX file systems. And I'll talk a little bit more about this, but basically just sort of the standard type of interface you're kind of used to of interacting with files is what's called a POSIX file system. But when we start talking about file systems, this notion of looking at the directories and files that you see on the systems you might be interacting with, this isn't a misconception comes up with the file system hierarchy that you see, right? So this file system hierarchy standard, FHS, is the conventional sort of layout of the directories and files that you'll see on Linux operating systems, right? That you're interacting with on these HPC systems. This isn't necessarily a file system, right? This is just a standard of how different directories and files are laid out across any computing system that uses sort of a Unix-like operating system of where things go and why is all sort of explained with this standard, right? It's not too important to dig into a bunch of the details of like, this standard. But there are certain directories that are important to you on any system that you interact with. And the most important one, and the one that's the most obvious to start with, is your home directory, right? So this is in the /home part of the FHS system, where you'll find your home directory, right? So what's a home directory, right? If you're new to working on these multi-user shared systems, like HPC systems, right? You have to have a particular space for every user to store at least some directories and files to organize their data on it, right? Very, very straightforward. And this is what's known as your home directory, right? And I'm signifying this with the $home because this is the environment variable that points to where your home directory is located, right? While the standard is in /home in the FHS, as we saw, it doesn't mean that the system that you're working on actually stores your home directory there, right? For many different reasons, different systems might put it in a different path, okay, because of what type of file system it's on, just how they want to organize things. But at the end of the day, this environment variable is what's going to be pointing to that directory. And as if you're already started working on HPC systems, you'll be very aware that typically I can't think of a system that doesn't have this, but it's your working directory on login. So when you log into any system, that is your home directory, right? And typically the use case for your home directory is kind of where you want to stage in and install software. You want to create and write and submit your batch job scripts from that directory, and store any sort of small essential input files and output files from your job. So typically I'll put like, very small input files or store the standard output files from the jobs that I run in my home directory. Now, in most cases on HPC systems, right, the home directory will have a limited amount of storage available, right? This is usually in the tens of gigabytes, maybe hundreds of gigabytes range, right? So you're limited on the amount of total storage in your home directory. There's a couple of reasons for this. Usually, if there's any file system that's going to have some sense of a backup of the data that's stored on that system, it'll be in your home directory, right? So usually as operators of HPC systems, we're assuming your most critical files are going to be stored in your home directory. It's kind of the general assumption, right? Different systems might tell you to put certain things in different spaces, but this is really the general use for your home directory. Yeah, but because of the limited amount of storage, right? Depending on the type of work you're doing, if you need to store large amounts of data, reading or writing large amounts of data, there's going to be other types of file systems on that HPC system where you're supposed to do that, right? And so again, this kind of just highlights, just by looking at your home directory and thinking about how to use it, sort of already implies, on most HPC systems, right, there's going to be multiple types of file systems that you need to access and use for different reasons, right? But this is sort of, home is pretty generic, and this is kind of the highlights of what home is for and sort of its limitations. Okay. Now, so we've talked about the home directory, right, and what it's used for, but we haven't really talked about, what type of file system it's sitting on, right? Right. It's that was just part of the FHS, right? The hierarchy standard, right? Um, and there's multiple types or categories or classes of file systems that you'll run into on an HPC system, right? And the two categories are local versus distributed file system, right? So I mentioned the word POSIX, right? That's sort of the type of interface to a file system, right? Um, but how and where the different types of data live is what defines these categories, right? A local file system stores files on a storage device that's attached directly to the same computer, right? So it's like your laptop, your laptop has a hard drive in it, right? Your all the files on your laptop are probably sitting physically on a storage device within the chassis of the laptop itself, right? That's what, and the type of file system that's your operating system's using will be a local file system, right? So the operating system is accessing that local hard drive in your computer, right? When you get to an HPC system, the the main category that is going to be new to you is these distributed file systems, right? Which provide access to files across multiple storage devices over a network, right? So these distributed file systems allow you to store files and share them across the whole system, right? Essentially, when you store data on these systems, it'll be available to any of the compute nodes that you might access on an HPC system generally, right? That's kind of the idea. So you want to store data that can be accessed from anywhere that you're doing computation, right? That's kind of the idea, right? That's what these distributed file systems are generally used for, right? No, but the key difference here, right, is it's over a network, right? So you get this overhead of having to talk over the network every time you want to access um, your files, right? Which is very important, right? That's, you can imagine every time you access a web page over the internet, it doesn't necessarily load as quickly as a file that you might access locally on your web browser, right? On your laptop, right? You can see where the problems start to arise when you start interacting with distributed file systems, right? Okay, so if you are on a Linux system, or if you have a Mac, this should work as well, I think. Right, the df command, if you just want to explore a system and have a command to look at what the different types of file systems are available, this df command is the standard command that will display sort of some of the information about the different file systems that you have access to or are at least mounted on the given system that you're looking at, right? So this is a quick snapshot of one of the log nodes on Expanse, just looking at sort of the top entries that come out of this df command. And you can kind of see here, they give you the name of the file system, the type of file system, the size, how much is being used, how much is available, and kind of the paths of where these things are mounted. So you can see here where I have the yellow arrow, I'm pointing to the home directories of Expanse, right? So we talked about the home directory, it's in /home. Well, on Expanse, not exactly. Every user has a particular home server that their directory is actually coming from, right? So I'll talk a little bit about this later, but right, you can see the type here of the home servers are NFS, right? This is a network file system. So this is one of these distributed file systems where your home directory is actually served over the network to any of the compute nodes that you're accessing on Expanse, or in this case, on the login node. So you can see here how things start to get a bit complicated, right? That, not only everyone has a home directory, but everyone has a different home directory server. So sometimes if you're interacting with an HPC system and you're having problems, with say latency or accessing, say, your home directory, but you say your lab mate isn't having a problem. It could be that you're on different servers and one server is having a problem than the other home server, right? So diagnosing problems, starts getting more complicated. You start throwing in more and more file systems in different systems. Okay. Another important concept when you start talking about file systems is quota or disk quota. And this is on most file systems you interact with, you'll see some sort of limit. As I mentioned with the home directory, you'll have some sort of quota that you're assigned by the system administrator, whoever is managing that file system that you're interacting with. And usually there's a limit on the total storage, obviously, right? Because at the end of the day, every storage system, every file system has a physical amount of space that you can access, that anyone can access. So you have to divide that up in a reasonable way and allocate it to each individual user. But there's also something, you'll also be limited usually on the number of files you can actually store on that file system. And that's what's known as an inode limit, and I'll talk about what an inode is later. But those are sort of the two main quotas that any file system you'll probably have some sort of restriction set up. Now, one of the problems when you're working on HPC systems is they're all different and they all have different types of file systems. And even if they have the same types of file systems, how they want you to look up the information about your quota or how much space you're using can be different. And so really, if you're trying to look up some information about the different file systems and what the quotas are and what they should be used for, the best place to start is really the user guide for your HPC system that you're working on. And so I've just put a link here to the storage section for Expanse as an example. But yeah, unfortunately, things vary, and by system and by type of file system, and just by the team that's running the system might have their own sort of custom tools that they want you to use to look things up for whatever reason. But there are, again, some standard commands you can use to poke around and get information about how much space you're using, for example. And this is the du command. So this is a standard Linux command that you can run on any of the systems you have access to. It'll be there by default. And basically you just point du at, a specific directory, and it'll run through all the files and compute how much usage you have. So how much space you're currently using in that directory, essentially. So in this case, I have an example here. I'm just showing running du on my home directory, which is kind of what I do a lot on Expanse. When I'm working with users, it's kind of the only option we have to look up how much space you're using in your home directory. There are sort of quota commands for certain home directories on different systems you might run into, but we don't have that available on Expanse. So I'm often running du a lot. A lot of errors people see will just because they ran out of space. They've hit their quota in their home directory because it's small. It's like 100 gigabytes in expanse, and so they'll run out of space pretty quickly, and then jobs will start failing because it's trying to write to a space where it doesn't have any room left, right? And so this is kind of one of the most common errors we'll see. Um, yeah, so DU is an easy way to check how much space you're using in any directory, regardless of the file system. The only problem with it, as I put a note here, is it can take a lot of time depending on the total number of directories and files you have. Again, the more, as I'm trying to highlight here, the more files, the more directories, um, creates more overhead in all of your interactions on any file system. And different file systems are susceptible to increasing numbers of files and directories and things like that whenever you're running commands against them. But this kind of gets to this metadata issue that I was mentioning in my sort of goals for today. All right, let me check my time. 2:28 questions. Homegrown Doug commands. Okay. I'll have to check that out. Thanks, Sanjay. I guess there's a multi-threaded version of DU. Okay, data storage and devices and systems. So what I want to talk about a bit in this section is sort of some of the underlying technology and things that you may or may not be familiar with, and sort of how they break out into how they're used and how they're sort of integrated into the different file systems you'll be interacting with. But this is sort of the basic definition of a computer data storage system or device, right? It's really those underlying physical hardware components that are installed inside any sort of compute node in your HPC system or in your laptop. Right. It's really the components that make up the underlying technology that any file system will live on, right? And this is a common figure that you'll see when you're learning about how to interact with systems in a performant way. This memory hierarchy separates sort of the different types of storage you have access to on any given system based on sort of the response time, like how fast is the different types of storage technology that you have access to and that you can interact with, right? And so basically there's two large classes of storage that I'll talk about here in a second, but you can kind of see here, for the primary storage is storage that's sort of active and what's called volatile storage, right? I'll have a definition for that in a slide or two, where the storage is sort of active and used while, say, your application's running, right? Versus sort of these higher capacity, slower accessed storage devices, which are non-volatile, is where you sort of store data longer term, right? And different types of technologies have different speeds, and so they have different use cases. So there's always a sort of this hierarchy of like where you put data when, right? Depending on how your application's running, right? So usually you want as much data as possible in the fast primary storage while your applications are running. And as wind down your application, you want to save any important data from your jobs that you're running on an HPC system to the different types of non-volatile long-term storage and file systems that are used there at these slower cycles, right? And yeah, there's kind of the four key measures here of a storage system is sort of kind of obvious, but how much can it hold? How fast can it, how quickly can you write data to it? How reliable is it? Right? If you're trying to archive data for a long time, right, there's different types of technology that you might want to use for that. And scalability, like how much data will obviously determine where you can even put that data, right? You can't put petabytes of data in memory usually, right? So sometimes you need to sort of have sort of a hybrid strategy. But anyway, yeah. So memory is kind of the one of the most obvious ones that you'll use, obviously, every time you're running an application. But right, these are sort of the fastest storage where you can actually put a file system. That's kind of why I highlight it, right? So this is where large amounts of data can be stored for, again, immediate use for your application, essentially, and next to the access for the CPU, right? Or in case of GPU memory, if you're using GPUs. So one thing that's different about memory on HPC systems versus, say, your standard commodity hardware that you might find in your laptop is there is sort of error corrections for the data that's stored there. So it's kind of why these things cost a little bit more if you ever look up pricing on memory modules for HPC systems versus standard sort of home desktops or laptops. And again, yeah, I mentioned this kind of on the last slide that memory is not cheap, so it's fast, but it's more expensive storage. And so if your application needs lots of data while it's running, you might have a hybrid strategy where you're storing some data on one of these slower file systems, more non-volatile storage devices, and part of the data is in memory, right? So you might be swapping back and forth between sort of disk and in memory, depending on the type of application running and the size of data that you're using. But yeah, again, the last note here is like this is kind of where you can actually set up sort of your fastest possible file system, which is kind of known as a RAM disk, which I won't go into detail here, but you can definitely check out the links. Now, when you're trying to understand the limits of the HPC system you're on, and right, it's always important to know how much memory that you have access to on any of these systems. But just a few things to remember, and this free command is kind of like the easiest way to look up how much memory is on a given system that you have access to. But just remember, on these HPC systems, usually there's dedicated nodes for different types of things. So like on Expanse, we have login nodes, right? So that has a certain amount of memory because it's a login node. There's standard compute nodes that only have CPUs, and that has a certain type of CPU and a certain amount of memory. Then we have GPU accelerated nodes, which have a certain number of GPUs and different types of CPUs and different amounts of memory, right? So you just need to remember that different nodes in an HP system will have different amounts of memory, and you want to make sure that you understand the different limitations for the type of compute hardware that you're trying to access and utilize. So I've already kind of used these definitions a little bit, but just to cover them again here, right? So again, in addition to the sort of different tiers of storage, right? There's really two general classes, right? So what's known we call sort of the primary storage is also known as sort of the volatile memory. So this is like all of the storage devices that you access on a system that requires power to maintain that storage, right? So if for whatever reason there's power interruption, right, the data there will be lost, right? This is what sort of primary storage, active storage, whatever you want to call it, right? It's sort of only on and usable while there's power, right? So that's why it's called volatile, right? So the non-volatile storage is kind of what you're kind of maybe more naturally think about as where the file systems live, right? So this is sort of the longer term storage that can, even if you turn off your laptop, the data is going to be stored there when you turn it back on, right? So that's this sort of persistent long-term storage, right? And there's, again, as shown here in the diagram, right, there's different types of technology and the different types of file systems that will live on those individual types of physical medium, depending on the use case, right? So for a long time, right, hard disk drives, these electromechanical storage devices were the main sort of non-volatile storage used in sort of every sort of personal computer, right? And even in um, high performance computing, compute nodes. They're not used so much anymore on individual compute nodes, right, as what we call node local storage. So most HPC nodes will have a local file system, a local storage that you can access while your jobs are running, while your application's running, for this faster access to storage, right? At least temporary storage, right? So you don't have to use these distributed networked file systems that are a bit slower, right? Because of the network interaction. Um, but these still play an important role in HPC because they're typically part of one of those distributed file systems, right? So not only does the network sort of get in the way of the performance that you have access to, with these distributed file systems, but these slower sort of what we call spinning disk drives, right? Have physical limitations of how fast they can spin, limits how fast you can read and write data to them, right? And that limits how those distributed file systems that are using this hardware, um, how fast they can go, right? And so just something to keep in mind. Um, Most of the time these days, the node local storage that you'll see in any HPC compute node will be based on SSDs, so solid state drives. So these are completely integrated circuit devices, right, that can store your just data persistently. So pretty much all your laptops these days will have, I mean, no, they definitely have some sort of SSD as your primary store, non-volatile storage on your laptop, right? So same with um, HPC compute nodes. At the very least, there'll be one of these in every node for the operating system that's running that node, right? And so um, but your use case of how you'll interact with SSDs on HPC systems will usually be with this node local scratch disk, right? So there's some temporary space that most systems set up on every node where you can read and write data to very quickly on one of these SSDs while the job is running, right? But um, and you'll also see in some of these distributed file systems, they'll have a storage tier in sort of a multi-tier distributed file system where the data that's most hot or most active, right, interacting with the file system will be stored to some sort of SSD first before it gets sort of maybe backed off to spinning disk or something else. And yeah, magnetic tape. So magnetic tape is kind of exactly what it sounds like. It's just a big drum of magnetic tape that people still store lots of data on. And it's still pretty important in the sort of storage hierarchy in HPC. It's really used for archival and backup use cases. So even in Access, you have access to Ranch at TAC, I think is still um, an allocatable system. And so if you need tape backup for your um, data, that's sort of the largest one in the sort of NSF access system that I'm aware of. And so, yeah, again, why do you use tape? Because it's cheap and you can store petabytes of data pretty easily, right? The downside is it just takes, it's harder to get data off because they have to find the tape and run the data off the tape and get it for you. Okay, check my time here. 20 minutes left or so. Let's see if there's any questions. Looks like there's some discussion. Okay. Some people are getting into the weeds on the du command. Okay. And John Paul asks, will we cover sticky permissions and inheritance? Did I miss that part? No, I mean that's sort of way beyond the level that we're teaching here. So, and yeah, ACLs would be nice to discuss. That might be in sort of some of the hands-on material eventually. But yeah, that's kind of far beyond the scope of today's talk. It's really trying to make the definitions here and sort of general overview of data storage and file systems. So yeah, as I mentioned a few times, right, the most common type of file system you're going to interact with is, or the interface to all of these file systems that you'll interact with is a POSIX interface. And so these POSIX file systems are organized in a certain general way, right? As I mentioned earlier, they'll all have these operations, create a file, change the permissions, open file, read data, write data, and so on. But it gets a little complicated, and actually understanding how these things work is not necessarily critical for your work, but having some sense of how things are laid out and organized in the different terminology, um, you know, could give you insights into sort of how things work on the systems you're interacting with. In particular, and so what I kind of just want to step through some of the definitions of what's going on here with these diagrams, right? I mentioned briefly inode before. There's something here called data blocks. There's directories and files, and so they're all sort of related to one another in a certain way. And I've also mentioned metadata. So just to walk through some of these definitions. So a block is really the physical sequence of bytes that's laid out, and sometimes it's called a record, and it has a certain size. So basically, this is sort of the physical. I think even in the in the hard disk drive here, the images here, these I put like a electron scanning microscope picture here of sort of what the physical medium looks like on the actual spinning disks, and you can see these little regular structures, right? These are like the physical actual blocks the on the disk itself, right? And so every storage device that supports block storage will have these sequences of bytes that you can store in, we call them blocks, right? And there's a certain size to these blocks, and the POSIX file systems sort of organize themselves around this notion of a block, right? And these sequences of blocks. And so, yeah, as you can see here, I've kind of listed a few of the characteristics. So each block usually has a fixed number of bytes. In most systems, that's sort of usually 4 kilobytes. And let's see, all the sequences, all the bytes, yeah, all the bytes are sequential within a block. So, as you write a block, every byte that you write is, sequential. But as you'll see, right, I mean, files are made out of blocks, right? But not all the blocks need to sit next to each other on the same physical part of, say, the spinning disk, right? It's the file system's job to understand where the different blocks are on the physical medium to reconstruct your file, right? Essentially, right? And so that's sort of what the last point is here. The underlying storage systems are organized as blocks, and the file system tries to keep these blocks sort of aligned and accessible quickly together to reconstruct, say, your file when you access it, but doesn't necessarily have to be sequential. Inode. So this is one of the most important concepts that I would say most beginning users don't understand and don't know about, but it's like one of the most important parts of understanding why certain file systems don't necessarily or understanding sort of the limitations of file systems, right? And this gets to this idea that I mentioned that in addition to having a limited amount of space, right, a limited number of blocks you can put on any physical medium, right, there's also something called an inode, which is a data structure that describes a file system object, right, like a file or a directory. So every file you create and every directory you create creates an inode. And this is basically uh, what's used to provide the metadata about that file system object, the file or the directory, right? So it's all the stuff. There was some discussion in the chat about um, permissions and inheritance, and there's all sorts of metadata that are always tied to a file or a directory on a file system, right? So I've listed here kind of some of the metadata that an inode provides, right? And so there's always a timestamp of when sort of your file or inode was last modified, when the contents of the file were modified, the timestamp when the file was last accessed, the ID of the user who owns the data or the file or the directory. There's always in Linux, right? There's this concept of groups. So users belong to groups. And so there's always a group ID that's associated with the data, the file, the directory. And these different bits that were discussed in the chat and permissions and things that, we're not going to go into the details there. But so these inodes, right, track all of this information about the files and directories that you're creating on any given POSIX file system, right? And so you can imagine as you're accessing a file system, right, the operating system, requests like, I need this file. Well, the file system goes and finds that file, but it also has to look up, how does it look up that information? Well, it has to know about it gets the metadata about your file from the inode, right? And yeah, so right, every time you access a file, there's all this other information that might need to get looked up in the file system. So if you have lots of files and lots of directories, there's lots more information to look up, right? So this metadata becomes overhead in some cases if you're doing too many writes and too many reads to too many files too quickly, right? And then if it's all over the network, then there's all these network calls. So understanding that, every time you access a file, there's all this other stuff that needs to get looked up and understood by the file system is how you run into some of these performance bottlenecks, right? If you don't access your data in a reasonable way, you might create a lot of metadata operations is what we would call it. Good. Okay, 10 minutes left. Let's get moving here. Okay, so directory, right? So directory is also kind of a special object in POSIX in the sense that uh, all it does is contain references to files, right? So it's not, um, it's and yeah, I put a note here. Each POSIX file may have its own implementation of a directory. But again, it has basically it's the structure that tracks the files and the inodes to the files that are associated with a given directory, right? So it's sort of yeah, it's what if you look at the figure here, right? The directory entry, all it keeps track of is all of the inode data and pointers to where the blocks for the file live on the physical medium. Right? So directory. So that's sort of directory is sort of special file system object. But file, right, is just again a set of blocks used to store the data. They don't have a name, right? The name of the file is actually stored in the directory, right? Object. And yeah, they are a set of blocks that can be either directly referenced from the inode or indirectly referenced from another data block. So if you look at that structure there, there's kind of you have a hierarchy of how the blocks are referenced. And yeah, so again, the idea here was to give you sort of a sense of sort of the complicated nature of the concepts once you start digging into the details, right? But that's sort of the general overview of what a POSIX file system is made out of. It's blocks, inodes, directories, and files, right? And all of these file systems that I'll touch on here before we end are POSIX file system, right? Because all it is really how it keeps track of that sort of POSIX objects and how you interact with them, right? And This here is an example of a command line utility for a Lustre file system, which is a POSIX file system. And here I'm looking up, they actually have their own quota command, right? So if you're working on a Lustre file system, this allows you to look up your sort of quota for the Lustre file system you have access to. And here on Expanse, I'm looking at two different, so I'm running the quote command two different ways. So we have a scratch location of the file system and we have a project part of the file system. So the scratch is kind of used for short-term temporary storage. And you can see here that I'm using 15 terabytes and I have, sorry, what was that? 12 million files there. But you see there's also these limits, right? The limit is 0 in Scratch, so there's no limit there. In the project storage, you can see here there's, I'm using about 23 terabytes and there's what, 16 million files, but there's a limit of 50 terabytes on that part of the file system, right? So that's looking up the quota. In this case, it's actually showing that this other limit here, which we used to have but don't right now, was the inode limit, right? So you have both the space limit, right? The total amount of storage you can have, and there's actually also you can set the inode limit on Lustre, which is not here. Oh yeah. So here, yeah, I'm showing. It's probably just because the two accounts have different permissions. So yeah, here on this second slide here, you can see that the standard inode limit on this Lustre scratch space is supposed to be what, 2 million files. So if you run into that, you're supposed to get an error message, right? And the reason for putting inode limits on Lustre is it's very bad at handling lots and lots of small files, which is kind of a common problem. Okay, few minutes left. So I'm just going to do a quick high-level overview of sort of the common file systems, and then show you this graph of a experiment that I did to sort of demonstrate why it's important to think about all of these issues about metadata, number of files, and things on the different types of storage systems and what they're supposed to be used for. Kind of brings everything together there. Okay. So yeah, so again, on any HPC system, you're going to have multiple types of file systems used for different things, right? So this is just a general overview of Expanse, and I've put the yellow arrows pointing to the 3 types of big storage systems that we have available on Expanse. So the middle one here is pointing to the actual physical, NFS servers where your home directories are located, right? Then we have, as we just saw, a Lustre file system. So this is a big parallel file system with about 12 petabytes of storage. Lustre is a pretty complicated type of file system I'll show you. Then we also have a Ceph storage system, which I'll talk about. And that's sort of not as widely used, but we do have it if you're interested in using it. Yeah, so you're always going to have on any HPC system, multiple file systems for different use cases. I'm going to skip over this and just get to the file systems themselves. So again, we talked about there's always going to be local file systems and distributed file systems. So local file system, ext4 is the most common local file system you'll see for Linux operating system. So if you run that df command that I started off with today, you'll notice that there's ext4 file systems located, say, on Expanse login nodes or some of the other nodes that you might have access to while your jobs are running. And those are the local file systems. And as I've mentioned here, you're going to have some node local sort of scratch disk, temporary spaces that people can use. So you can see that those are sort of highlighted here with the arrows. Yeah, so those are local file systems. Network file systems are going to be one of the most common ones you'll see your home directory served out of. This is kind of showing a diagram of how this works, right? Say if you're on a login node, that might be the client side here, right? And anytime you run in a command there that accesses files that are stored on those home servers across the network, right? It literally has to make these calls out to the other server to fetch your files and access the data at the client, right? So this really is sort of the most common, most popular distributed file system you'll see. And again, it's mostly used a lot of systems as your home directory. And so this kind of file system learn about if you're working on an HPC system. You can see here on Expanse, all the home servers are NFS. I mentioned Lustre on Expanse. This is a big parallel file system we have. And it's probably the most common and popular parallel file system on HPC systems. And you can see here in the diagram, it gets pretty complicated. All those Lustre clients are the compute nodes and the login nodes. So again, you have that sort of client side that you are accessing your files from. It all looks the same, like you have that POSIX interface accessing files and directories. But what's going on behind the scenes is all that data is the metadata is separated from the actual data in your files. And you can see there's this complicated dance of how when you access your files on a Lustre file system, it has to go to the metadata server. The metadata server needs to look up where that's where all of the inode data basically is stored, right? To then tell your client where your data is actually living out on the storage targets, right? And so there's all this dance going on behind the scenes of when you need to access files. And Lustre is really designed for writing large files, large amounts of data, reading and writing, right? And it's from many clients. It's really meant for sort of like weather simulations and big, large scale traditional HPC applications. What it's not good at is reading and writing lots of small files very quickly. And with a lot of the AI workloads going on today, where you have lots of, say, millions of images that you want to train a model on, dumping a million images or, which are, maybe 100 kilobytes or, maybe megabytes at most, onto a Lustre file system is just going to grind things to a halt, right? If you try to dump millions and millions of files onto a Lustre file system, it's just not designed to handle that, right? And so this is where you need to think about carefully where you place your data and how you package your data as you're accessing it on these systems. And so that's kind of my main public service announcement here. Be careful, especially when working on Lustre. Ceph is a newer, well, not newer, it's probably 20, 25 years old now, but it's more of a storage system that provides different types of actual file systems. So it supports block and file storage, but also is popularly used for object storage. So object storage is different than traditional POSIX file systems. It's more, object-based storage is kind of like cloud storage, Amazon S3, if you're familiar with it. It supports everything from, POSIX file systems to object storage. And so you might, and it's pretty commonly seen these days as one of the alternatives that you'll see as another file system that's used on HPC systems, like we have it on a couple of ours. And so it's an important one to sort of get familiar with, and you might run into. And the one thing that Ceph does nicely is things like Lustre are very expensive and high performance. And so those systems don't usually have a backup of the data that's stored there, right? There's only a single copy. Ceph has some nice features where it provides some fault tolerance and high availability of the data that, if parts of the file system go down, you're probably not going to lose data, where Lustre is very, very particular. If something goes wrong, everything goes wrong. Usually, and so it's a bit Ceph is just a bit more robust for storage. I would trust it more with longer term storage than, say, Lustre. Okay, and there's a whole space of many different file systems. Some of these are like different commercial versions of NFS and other types of repackaging of different file systems. out there that you might run into. And it's a big space these days, especially because of all the AI workloads and things that run into those problems that traditional high performance file systems like Lustre can't handle, right? So there's a lot of work in the space on the commercial side that is going on right now and that you might run into on different types of file systems. Like Vast is one that we've just put on one of our newest systems and we'll have running. Okay, so I'm going to end with this last graphic just to highlight why all this is important, why understanding some of these details and definitions and terminology and sort of how they all relate to what comes out the other end when you're running your workloads on HPC systems. So this was an experiment I ran, taking one of these AI data sets, this ImageNet data set, which has basically 1.2 million images. It's about 130, 140 gigabytes of data total. And part of the workflow to train a model on this stuff is usually you want to pre-process this data, this million images, into a set of files. In this case, for TensorFlow, these TF record files that are, transforms and packages those million files for training into like 200 files that are more easily accessible and more native to sort of the TensorFlow tooling. But you still have to sort of unpackage, unzip a million files from like a tarball and then process them into these record files. So you have to do this pre-processing before the training. And what I did is actually did that experiment for you of dumping a million files, 130, 140 gigabytes, onto the different file systems we have on Expanse and see how long it took to process those raw images into these TF record files. And the only thing that changed was the underlying file system that it was run on. So you can see here on the node local scratch, that local file system, really fast, right? So it took under an hour on average to pre-process the data set. Doing it on my home directory on NFS, right? It's going over the network, it's gonna be a bit slower. The back, I don't even recall necessarily what is it spinning disk or is it NVMe backing our home directories? I think it's spinning disk. I don't really remember. But it took under 10 hours, like 5, 6 hours on average. Go to Lustre, some of those outliers are going over 100 hours, right? So you can see just because of the metadata overhead and the network overhead and the complication overhead of how the storage systems and the file systems actually work changes vastly the performance that you can see on any of the things that any of the workloads that you might be running on the system. So you really do not only need to understand what the different file systems are used for, but how to package the data, right? So in this case, like you don't want to unpackage a million files onto Lustre. What you want to do is copy that tarball that has the million files in it, that archive file, bring it to the local scratch disk, unzip it there, and then process the files. Take what you need and then transfer it out at the end of the job, right? So you have to understand how to sort of place your data in different formats on different storage systems for different reasons because of all these complications of the file systems. Okay. So I think I'm going to stop there and take questions. I'll leave up this best practices stuff if we want to talk about it, but I think we can stop the recording there, Cindy, if you're still here.